again, and welcome back to my channel. And today we're going to do the third and the final part to this low-cost tape preamplifier series. Previously we discussed the basic topology of this particular circuit board and what needs to be done to make it work. And I also identified some areas where I should keep looking in order to make them even better. And I have spent some time doing that. So today we're going to look at the final, hopefully, set of changes you need to perform to this particular Marantz 7 Chinese production circuit board to make it suitable for your tape preamplifier project. When you look at the equipment rack you have in front of you, you can see the tape transport on the top. That's again TIAC 25-2. It's a very, very good transport. And right below it, you can see the case, the black case, where the head preamplifier resides. And I still have to make some final touches, cosmetic mostly, about the power switch and power light, but it's basically in the final stage in terms of its circuit topology. At this point, I'm quite satisfied with its performance, and I don't think I will be making more changes. Right below that black module, you can see the McCurdy indicator box. And as you probably know, or you might know, it has two sets of indicators for each channel. The brightly lit ones are standard average meters, and the black ones are PPM meters. Unfortunately, the black PPM meter on the right has died. It worked fine in my office, but on the way here, something happened. I guess most likely the needle and the drive jumped off its support, and hopefully it can be repaired. But be it as it may, so that meter will remain idle at this point. It's not working, but the other three meters are functional. Whether you like to watch those meters or not, that's up to you. But they are there for now. I'm probably going to jump ahead of myself by saying that I do like the result I've obtained with this inexpensive vehicle. I think I mentioned last time, and I feel even more positive about this project after having done the final list of changes. And we're gonna go through that final list, and I will explain to you what they mean and how to approach them. And today we're gonna listen to two selections, two different tapes. The one on the machine right now you heard before. It is very good jazz recording. And the other one will be very different. It's going to be a classical piece, classical string trio. And I hope you like both of them. I think they do sound very, very good on this particular setup. So with this introduction out of the way, let's go back to our schematics. And I also brought with me today some test plots. I was working in my office today. I took this module there and I obtained some very nice plots. And I will explain to you what they mean, how to interpret them, and basically take them for the proof of the proper operation. So here once again is the amplifier circuit. And you might recall that early in this discussion, I told you that those components should be just removed up front. They're basically there just for the RIAA equalization, and in our case, we don't need those components. And I think I also mentioned to you that instead of this particular fixed resistor, we're going to put a trim pot in place. And that trim pot is going to be around 10K. And that should give you enough adjustment range. I also mentioned to you that this resistor here, you might increase the value of this resistor depending upon the inductance of your cartridge or your of your head. In this particular case, the combination of the tape head inductance and this resistance gives me the pole frequency of about 29 kilohertz. Is this enough? I think so. So at this point, I'm not going to increase this particular component because I do get very flat frequency response all the way into 20 kilohertz area. So apparently that's good enough. Now, if you are familiar with the way electrical engineers operate, you will know that pretty much any study of the circuit incorporating feedback starts with an open loop response. And in this particular case, it was very easy to remove the feedback. Let me show you. Basically, you just disconnect this particular component. Those two are already gone. And in this case, your feedback loop is open. And the top plot on this chart is an open loop response of this preamplifier. As you can see, it's got a fair amount of gain in mid frequencies, about 70 dB of gain, which is good. You're probably going to need 50, 60 kind of dB gain, a little bit more in the low frequency range. So I would like to see a little bit more, but we can work with that number. As you look at this characteristic, you can see it rolls off noticeably in the low frequency area. I would say this is about 3.5 dB drop at 20 kilohertz frequency. And that's going to affect our response because you can see this was the first pass of IC curve, and it comes dangerously close in this area to the open loop response, so it pretty much runs out of available gain, and therefore it starts rolling fast. So something needs to be done about this low end area. Specifically, what should that be? What is the component that's limiting our low frequency response? And immediately this capacitor comes under suspicion because of its fairly low value. It's probably okay for most applications, especially, well, it was designed, what, 60 years ago? And things were different back then. But today we expect more. And the first step to investigate would be increasing the value of this capacitor. And here it is. First, we see the response we had on the previous chart, and here you see it's sizable roll-off we would like to eliminate. And as a way of removing this drop, I put larger capacitor in parallel with this one. And as you can see, the response in low frequency area is now almost ruler flat. And that's a very, very good result. One other thing you notice when working at this open loop response subject, and that's the stability. And it's very, very pleasant finding here to see that the preamplifier is very, very stable. In my experience with this particular piece, it's never gone into oscillation, which is a good thing to have. Sometimes you have to fight the oscillation and your life becomes much more difficult. Not in this case. And like I said, this simple measure, actually that number is not correct. The final additional capacitor was 0.22 microfarad. And that produces the flat response you see in here. But going back to the first plot, we observe here that the response, which is IC EQ response, rolls off very rapidly at low frequency. And yes, we've done something here, we made it more straight, so you can expect that some straightening will going to happen here as well. But is it going to be enough? No, I don't think so, because you definitely seen the pole here at about frequency of 50 Hertz. And that pole is correct one for NAB equalization, but for IC you need to continue going straight into low frequency area without any roll-off. That's an ideal idea. You're probably going to start rolling off at some point, so in my mind, if it happens at below 20 Hertz, then you've done your job. So let's look at what controls this particular 50 Hertz pole here. And it is clear that those two components here, their product gives you the frequency of about 50 Hertz. And it needs to be reduced. How to reduce it? There are a couple of ways of doing this. One would be to increase the capacitance of this capacitor. And the other one, increasing the value of this resistor. Which one is preferred? Let's see what happens if you go after the capacitor. Let's say you have this response. With a pole at 50 Hertz. And you would like to move it to the low number. Sure, you can increase the capacitor. That's a C1 curve. And let's put C2, which is much bigger than C1. And what you're going to get is this plot. So you say, oh, well, it's good. Now this rolls off at 20 Hertz. So I've done my job. Well, sort of. Because if you draw this line at, let's say, any frequency, let's say it is 400 Hertz, you see sizable drop in gain. Is that going to be acceptable? Probably not in this case, because as I mentioned before, we're already kind of low on gain. Would be nice to have more. So cutting gain like this just to get reduction in this pole frequency is not necessarily a good way. In some circuits, that may be the only way you can use, but in this one, fortunately, you can do other things. If increasing the value of capacitor doesn't give you what you want, then you should go after this resistor. And your first inclination should be just double it. Why not? That should give you get you very close to 20 Hertz pole frequency. And if you go even more than double, then you get even lower frequency, which is good. The natural question will be whether you're going to run out of available gain. Hopefully not. But let's see what happens. Here we see the result of various values to that particular resistor. And as you can see, you have 600K initial value. Then it was kind of doubled to about 1.3, 1.5. I don't remember exactly the number. And the last chart, the last curve, shows that resistor removed. Now, the idea of removing that resistor entirely was mentioned to me by one of the participants here. That person seemed to be very, very well equipped in the area of electronics, and he suggested this particular modification. At first I was reluctant, because when you remove that resistor, all you have left is this capacitor. And you potentially run the risk of running into some unknown territory, because there are some unspecified parameters in this circuit, and the behavior of this capacitor into those unspecified parameters can bite you in the butt. But still, it's worth investigating. It sounds like a very good idea. And so it is. This is the initial value, 1.3, 1.5 megohm. Very nice improvement. Okay, you could stop here. You could see that this is probably pole somewhere in this area, 25 Hertz maybe. But you can go further and remove this resistor entirely, as that person suggested, and you see it straightens up even better, even more. So this is the curve I like, the last one. I tested the unit with this resistor removed several different ways, looking for some anomalies, and I found none. So at this point, I feel very safe recommending this particular modification. And I would like to thank that particular person for making this suggestion. It works very, very well in this case. And so, with all those modifications in place, this is what we have. This is almost perfectly good IC curve. Yes, it splits here a little bit tiny amount from the straight line, but it's very negligible amount. And considering this is a very old topology circuit with limited amount of open loop gain, I think that's a marvelous result. Don't worry about the split here. That simply means that one channel is still not perfectly adjusted at high frequency. And later on it was adjusted a little bit better, which is what you normally do with your calibration trim pot. So this particular curve is, I would say, almost perfect. And if I were building the modern circuit, I would say I probably still want to work a little bit in this area. But we're talking about very inexpensive approach here. And I would submit to you that this particular curve is going to be a whole lot better than what you can buy at some reasonable amount of money, maybe $2,000 and so, maybe even more. It's not like some very expensive equipment has perfect behavior. They always have some variations. And I would say this is among the best I have seen. And now I would like to play for you a wonderful classical recording. As I mentioned, it is a classical string trio, and I hope you like it. I like that recording very, very much. I hope it doesn't stop before I run out of recording space, but if it doesn't, I'm happy to see you again. And I hope you come again to this channel with your questions, with your opinions, with your statements, and we'll continue this search for some interesting items. Goodbye.